8.3 is geometrically defined vectors and applications. Let's start with some vocabulary. A scalar is a real number that can represent a quantity, such as a weight or a speed. Scalars would be things like 60 miles per hour or 3 pounds. That's all it is a number that represents a quantity. A vector involves both magnitude and direction. So these vectors, we are going to represent them with a directed line segment. The length of that line segment represents the magnitude, and the direction of the arrow indicates the direction of the vector. So the length being the magnitude or the force being placed on an object, and the direction of the arrow being the direction of the vector or the direction that that force is being applied to the object. Now the notation is this IT with a label of the arrow above it, and you can see that the first letter that is written is the initial point, and then the end is the terminal point. The T is where that arrow ends over. So they'll either write it like that, or in books you will see it as a bold IT. When you write vectors, you will need to go ahead and write the arrow above your notation there. Magnitude of a vector is written as the vector inside these bars. So we are going to learn how to find the force of a vector. Equal vectors are vectors with the same magnitude and direction. So here we have IT and NO vectors, and they are not in the same place, but they have the same length and they're going the same direction, and so they are considered equal vectors. We also have opposite vectors. These are vectors with the same magnitude, but they're opposite in their direction. For example, we see here vectors of IT and QM. IT and QM vectors are opposite vectors. They are the same length, so that means their magnitude is the same, and they have the same slope, if you want to put that on the coordinate system, but opposite in direction. And here we have vectors u and negative u. Those are opposite in direction, same magnitude, so those are opposite vectors. A fact is that every vector u has an opposite vector, negative u, and their sum has a magnitude of 0 and is the 0 vector. Another fact is that the sum of two vectors is also a vector, and the vector that results from these can be found two ways. The first one is the head to tail method. The way we do this is to take one of the vectors and place the other vector, its tail, its head to the other one's tail, and then we draw another vector from the head of the first vector to the tail of the second vector. And there you go. That is your resultant vector, m plus n, if you'd like to label that. Okay. And the parallelogram rule basically is making a parallelogram out of this the two vectors that you're given, and you copy them like such, and then once that parallelogram is constructed, then you draw, I'm just going to borrow this one up here, you draw the diagonal of that from the beginning to the end of that, and again you end up with m plus n. This also shows that it doesn't matter what order you add those vectors, you'll have the same resultant vector. So vector addition is commutative. Let's practice sketching resultant vectors. We have vectors u and v. We've been given the magnitude of the u vector and the magnitude of the v vector, and then we have the angle between them. So just go ahead and draw. Let's say we wanted to draw this first one. It's just going to be a sketch. It's nothing very accurate. So we'll say that this is a length of 3, magnitude of 3, so you draw it with a length of 3, and then another one at a 30-degree angle that has a length of 7. Okay, so a magnitude of 7 will mean that is a length of 7. We want to sketch the resultant of those two vectors. So what we can do with this 30-degree angle here, we can move this vector over, so we can do a head to tail, the head to tail method on this, and thereby and have the beginning to the end of the resultant vector, which is going to look something like this. Just either use a straight edge or just try to be as careful as you can when you're drawing that. And then we have this other example. We can use the parallelogram rule to find the resultant. So I'm going to just borrow those directed line segments here. I'm going to move this one so I can do my head to tail, measurement method of trying to put those together. And let's say that I'm going to go ahead and draw my resultant vector. We start at the beginning of this and go to the end of this one. Now you can tell, just conceptually here, let's talk about, you could tell that this is shorter than this one, but longer than this one. So think about if someone was pushing a box this way with 1,000 pounds of force, and someone was pushing, a machine was pushing the object this way with 400 pounds of force. This is the direction the box would go, and it would be of a force that is less than 1,000 pounds but more than 400 pounds. Those are the types of problems that we'll end up using vectors for. A vector that will counterbalance the resultant is called the equilibrant. So we're going to be finding equilibrant vectors. For example, u and negative u are equilibrant vectors. These get more complicated than just taking the opposite of a vector, because we're going to be using a couple of forces and then trying to find a third force that zeroes those other forces out. See, I have this vector length of 800. We can just go ahead and put it horizontally is a nice way to picture it. And this other tugboat is pulling the barge this way at a force of 920 pounds, and the angle between those is 23 degrees. So you're going to do a little bit of moving around. Let's start with our 800 here and move head to tail. So I've got this 920 right here. If I would extend that directed line segment out, I can see that this is an angle of 23 degrees, which means this angle inside here is 157 degrees. So this is the resultant vector of adding those two vectors. It goes this way. If we want to find the equilibrant, it's going to be the opposite of the resultant vector. So we want the vector that is going this way, okay, and has that magnitude of the resultant vector. So our work is set up here for us. First thing that we can do is find the magnitude, and the magnitude x squared, and since we have these two sides and their included angle, we can use law of cosines. I'll go ahead and say x is the square root of 800 squared plus 920 squared minus 2 times 800 times 920 times the cosine of 157 degrees. Make sure that fits all under the radical there. And when you put that into your calculator, you'll see you get a result of about 1,686 pounds of force. So that is the magnitude of the resultant vector, but it's also going to be the magnitude of the equilibrant. If we want the equilibrant, we are going to be adding these vectors to end up to be the zero vector. So the magnitude is 1,686 pounds of force. The next thing that we need to do is to find the direction of the equilibrant. So drawing our equilibrant vector is this way. It's opposite direction of the resultant vector, but the same magnitude, magnitude being 1686. And we have to find the angle between, if we would make this into our parallelogram, we have to find this angle right here. So if we could just find this angle right here, alpha, and subtract that from 180, this is 180, then we'll have the measure of that angle. The way the parallelogram is set up, that makes this an 800, makes this a 920, so we can find alpha fairly easy. We'll say that the sine of alpha over 800 is equal to the sine of, this is going to be 157 as well, sine of 157 degrees over the 1,686 that we just had. So we're going to cross multiply and take the inverse sine. So we're going to multiply both sides by 800 and take the inverse sine. So inverse sine of 800 times the sine of 157 degrees divided by 1,686, and then close the parentheses, and we get an alpha of about 11 degrees. We'll just round it to the nearest whole degree. Alpha is about 11 degrees. So if I take 180 and subtract that 11, I get 169 degrees for the direction of my equilibrant. This next example, we're going to find the force needed to keep a 3,000-pound cart stationary on a ramp that makes an angle of 15 degrees to the horizontal. Now we are going to assume that that 3,000-pound cart doesn't have resistance. Maybe it's on very free turning wheels. So it's a highly simplified problem, but it helps you to practice the skills to get ready for a more difficult problem later on. So let's do some drawing. We have a ramp here that makes a 15-degree angle to the horizontal ground, we'll say. And we have a cart that is 3,000 pounds. Now the force pulling down on that cart from gravity is that 3,000 pound magnitude. So 3,000 pounds magnitude is the force that's pulling it down. What we want to happen is to have a force pulling this way on the cart, okay, so that we can add that. We can even add it head to tail down here, like so, that we end up with an angle that is a right angle to the angle of the ramp. So we are trying to find what this force is needed, the magnitude of that vector, or the length of that directed line segment. So we'll do a little bit of work this way. We have, let me move my 3,000 over because it looks like it's labeling the wrong thing. This is 3,000, that vector, the magnitude of the vector going straight down from gravity. And this is at a 90-degree angle. So if that's a 90-degree angle and that's 15, that means that this is 75 degrees. All right, and then now, knowing that we have this and this as parallel lines and we have a transversal going through, this is also 75 degrees there. So now we can just use simple trigonometry, right triangle trig, to be able to figure out the length of this vector right here. And that's all we want, is the force needed. So that's going to be the magnitude or the length of that vector. So I have a right angle here. That means that this is the adjacent side and the hypotenuse. That would be my cosine function that I need to use. The cosine of 75 degrees is equal to the adjacent over the hypotenuse. So A is 3,000 times the cosine of 75 degrees, and just make sure that you're in degree mode. A will be approximately 776 pounds of force. Okay. This last problem we're doing is where we have a boat leaving a port on a bearing of 110 degrees. It travels 8.8 miles. Then it turns due west, going straight west, and travels 2.4 miles. How far is the liner from the port, and what bearing is it from the port at that point? So we'll draw a little bit of a picture here. We start out with 110 degrees, so they are going from the port. Remember that when they give just the one measurement, then they're talking about A to Z, 0 to 360 degrees on the bearings. So we've got 90 and 110. So 110 is this degree measurement. 110 degrees, and they go for 8.8 miles. And then at that time they turn back straight west and go this way and travel 2.4 miles. And they're wanting to know how far is the liner from the port at this point. So how far are they? And then what is its bearing from the port. All right, so we'll go ahead and set up this problem. We want to find x here, and I know this distance and this distance. Do we know anything else? Well, I do know that if this is 90, this is 20 degrees right here, and this east-west line and this east-west line are parallel lines. They're being cut by this transversal. So this is also 20 degrees. The alternate interior angles are equal. So we have 20 degrees there, and it looks like it's set up perfectly for the law of cosines. My x is going to be the square root of 2.4 squared plus 8.8 squared minus 2 times 2.4 times 8.8 times the cosine of 20 degrees. And once you punch that into your calculator, it comes up as about 6.6 miles from the port. All right, so we're 6.6 miles from the port. And now we also need to figure out what the bearing is on that. Let's say that we call this an angle B. We can figure that out pretty quickly given the information we have and what we found. So we could say that the sine of B over the 2.4 given is equal to sine of 20 degrees over the 6.6 that we just found. So we're going to multiply both sides by 2.4 and take the inverse sine, and I'm going to get angle B of about 7.1 degrees. Now we don't just take that as it is. That is the angle that is added on to that 110 degrees. So our bearing now that we are located from the port is 117.1 degrees from the port. And that does it for this section. You go ahead and take a try at your homework. Give yourself a lot of time to study this section. Let me know if you have any questions.